Today I'd like to focus a little bit more on a very important part thereof, namely iron absorption. So iron absorption. Now what you see here on this screen is a duodenal cell. So let's just put that here, duodenal cell. And this is the place where most of the iron absorption takes place. Now when iron comes into the body in the form of food, it comes in usually in two main forms, namely heme and non-heme iron. So heme iron, also often referred to as organic iron, coming from meat, for instance, or fish. And the non-heme iron, often referred to as the inorganic iron, and this is often derived from plant sources or vegetables and so forth. When you take in food, just in short, in the stomach, the acid in the stomach will start digesting the food, will release the heme from meat, for instance, and a lot of things can happen with iron through the food that you eat on its way to the duodenum. And I'll make another video on dietary iron and the different aspects thereof later, but today I would like to focus on how iron gets absorbed and eventually into the body, into the bloodstream. So let's take this duodenal cell here, and just below that we're going to put a blood vessel. Let's just draw a blood vessel here. So we've got two different forms of iron that we need to get absorbed. On the one side we have the non-heme iron, or we're going to draw it like this. We'll call this Fe3+, also known as ferric iron. Ferric iron. And then on the other side we're going to place heme iron. So we'll draw it like this, and in the middle there is Fe. Fe stands for iron, of course. So we need to get both Fe3+ and Fe iron into the cell, and eventually we want to get this to a molecule in the bloodstream called transferrin, which has the two seats, as I've explained in the one of my previous videos. And we need to get the iron from here, which is the lumen. This is the lumen of the gastrointestinal tract, to the bloodstream here below, where we want it to connect to transferrin. Now to do that is not as simple as it may look. There's a number of steps that you need to go through to get iron from here to here. Right, so let's start with the Fe3+ iron. Now Fe3+ iron is usually insoluble and very poorly absorbed. So you need something to change the Fe3+ iron into a different form of iron called Fe2+. So we're going to draw Fe2+ here, Fe2+, also known as ferrous iron, ferrous, and I often remember this ferric, like ric 3, ferric 3, and ferrous is almost like ferrous, like 2. It sounds very similar. So the ferrous and the ferric iron. Now to go from Fe3+ to Fe2+, which is the form that the body can absorb better, you need an enzyme. And we're going to place this specific enzyme right here on this microvillus on the border of the duodenal cell. And this one is called D-site B. The long name is duodenal cytochrome B reductase. It's also named ferric reductase. That's its other name. Okay, so with this molecule it will be able to change the Fe3+ into Fe2+, and the Fe2+ can then be absorbed by another molecule on the surface. And we'll give it a, let's draw this one here. We'll draw it like this. This one is called DMT1, or divalent metal transporter 1, DMT1. You can see the valency of the ferrous ion, the 2 plus, is divalent. It's 2 divalent. Iron is a metal. This is a transporter, so it's divalent metal transporter 1. And with this transporter, the Fe2 plus can get into the cell. Now, once inside the cell, it will go into a pool of iron. Let's draw it here. So here we've got a lot of Fe2 plus in the cell, and this is a so-called labile ion pool. The problem with this is, and this is also why the word labile is used, is that Fe2 plus can form reactive oxygen species once it connects with oxygen, and those ROS, or reactive oxygen species, and I'll write that in red here because these are like real terrorists. They can damage lipids and DNA and membranes and everything else. So this is a little bit of a dangerous pool that we have here. So we'll have to do something with this, and I'll come back to that. Let's leave this labile pool to be lying around here in its labile form for a while, and first see how we get the heme ion over here into the cell. So this is heme ion. You can see in the middle there's the iron molecule there, and the heme ion binds to something. Now, why do I say something? The reason is because we're not exactly sure what this is. So let's just say there's some kind of a receptor here for this heme protein, something that it can bind to that will allow it to get into the cell. Now, there are different theories. Some people said this is HCP1, also called heme carrier protein 1, but that's not so clear. It seems like HCP1 may be more involved with folate absorption than with heme absorption. More recently, they have found another possible molecule that could be responsible for heme absorption, and this one has got an even longer name. It's called FLVCR2. Now, what is that? What on earth is this? This is feline leukemia virus subgroup C receptor 2. Now, that's a mouthful, and I think you can forget that. Just to let you know, there's different hypotheses on what exactly this molecule is, but that doesn't matter. The reality is there is some heme carrying protein that gets the heme into the cell, and once inside the cell, this ion connected to heme, this ion obviously has to be released. Now, we should probably have drawn this ion in yellow as well, because this is also the Fe2 plus that we're going to want to release from the cell. And there is another enzyme here that will do exactly that, and it is called heme oxygenase. And the heme oxygenase will release this Fe2 plus ion from heme, and we know what this looks like already, and this Fe2 plus will join the labile ion pool. So now we've got lots of labile ion here coming from, as we saw, inorganic or non-heme ion forms, or from the heme ion forms. Now, once you have this labile ion pool, there are 3 possible things that can happen with this ion. Well, first, we said it's labile, and the body doesn't want these labile molecules to be lying around, so it needs to be placed in a safe spot. So let's just say we said 3 things can happen, and I'm going to put it like that. First thing that can happen is it can be stored. And for storage, we've got this molecule called ferritin. Ferritin. And ferritin can store about 4,500 of these iron atoms. 4,500. Okay, so we can fill this molecule up with iron. Right, so that's one way. So when it's in this ferritin capsule, it can be reutilized later when needed. So iron can go in and iron can go out as well. So it can go both ways as needed. But at least when it's inside the capsule, the iron will not damage the rest of the cell. The second thing that can happen is that the cell can use the iron for its own needs. So let's draw, for instance, a mitochondrium here. Okay, so let's say this is a mitochondrium, which, as you would remember, is the energy production area of the cell, but there's also a whole lot of enzymes in here, and this is also where heme synthesis takes place. So the iron can go to the mitochondria and be utilized, and it can be utilized to make enzymes and to make heme. All right, but as you can see, we've now got storage iron on this side here. So this is storage. We've got utilization, but we still haven't got iron that moved from here in the lumen of the gut to the bloodstream. So the third part of the iron will be exported. Right. And how does that happen? Well, there is another molecule, a very important molecule as a matter of fact, on the surface of the duodenal cell, on the so-called basolateral surface, and this is called ferroportin. Ferroportin literally means, as you can see from the word, iron door. And the iron that is coming out of here, the Fe2+, can move through the ferroportin into the bloodstream. The only problem is that the transferrin here can only carry Fe3+. So we want Fe3+ to go onto the seeds here, but what is coming out is Fe2+. So let's just go back to the Fe2+, and let's see how we can get that changed into Fe3+. I'm going to draw another ferritin molecule here, transferrin molecule I mean here. And now we need something else. There's another molecule which is associated with the ferroportin. And as this Fe2+ comes out, the little yellow dots, it can be changed by this molecule, just like we saw the way the dicytochrome B, the ferric reductase, changed Fe3+ into Fe2+. This molecule can do the opposite. It will change the Fe2+ back into Fe3+. Fe3+, and this Fe3+ can now bind to the transferrin. So by now you must be wondering what this molecule is called, and the name of this is hephaestin. Let me just write it here. Hephaestin, and you can hear that it is named after the Greek god of metals and fire, Hephaestus. He was supposed to be the one that worked with metals. And apart from hephaestin, there's another molecule in the plasma called ceruloplasmin. Ceruloplasmin. And as you know, this is also a molecule that can carry copper, but ceruloplasmin can do exactly the same. Both hephaestin and ceruloplasmin can change Fe2+ into Fe3+. The only difference is the hephaestin is bound to the membrane of the duodenal cell and associated with ferroportin, the iron door, while ceruloplasmin is moving around in the plasma. This way, the Fe3+ can bind to the transferrin, and the transferrin can take the iron to red blood cell precursors and other cells where it can be incorporated into the production of red blood cells, for example. And now we get to the very last component, but probably the most important component of iron absorption. And this is, how is iron absorption controlled? And the big issue is that iron absorption is almost completely controlled at the level of ferroportin here. And there's a molecule produced by the liver. I'm going to draw, that's the liver there, by the liver, called hepcidin or hepcidin, depending on which part of the world you come from. And hepcidin is usually produced when there is too much iron in the body. And when that happens, the hepcidin will go and will bind to ferroportin. The ferroportin, once bound to hepcidin, will be moved into the cell, away from the membrane, and inside the cell it will be destroyed or broken down. So this will be broken down, so there will be less ferroportin available on the membrane for iron absorption to take place. On the other hand, if there is very little iron in the body, so let's say the iron is low, then the liver will produce less hepcidin. And when the hepcidin is not there, ferroportin can remain on the surface of the duodenal cell and more iron can be absorbed. And there are many examples of diseases that influence hepcidin levels up or downward that causes either an increase or a decrease in iron absorption. But I'm going to leave the details of the regulation of iron absorption through hepcidin for other videos.